Converting a complex number in rectangular form to polar form. So let's do an example. Let's use this one here, 3 minus j4. First thing we'll do is just visualize this in the Argand diagram. So we know that the real part will be represented in the x-axis or the horizontal axis, the real number axis, and the imaginary part of this complex number, including that negative sign, will be represented in the vertical axis, the imaginary axis. So negative 4 is down here. So we see that our complex number, this is what we have. And very important, we draw that line now. So what we are after is, for the polar form, is actually calculating this length of this line that we drew from the origin to the point, and that is called r. So just bring a little arrow here, r, which is the modulus or the length of that segment, and the r that is up here, and the angle or the argument theta, which is, as if we go anti-clockwise from 0 until we hit that segment, or so that would be an angle greater than 180 degrees or greater than even 270 degrees, and but positive because we're going anti-clockwise. But if we came this way here, we would have a smaller angle, less than 90 degrees, but a negative one because we're going clockwise. So let's see how we calculate this. And it's all about a triangle that we can visualize here, and I'll draw again. So we have our complex number there, so we need to find that length, knowing this is 3 and this is negative 4. So in terms of a triangle, we can visualize here this green bit would be the hypotenuse of the triangle. So this measurement here being 3 in terms of measurement, and this one here being 4. We know it's negative 4 in the diagram, but for the sake of the measurements, it's 3 and 4. So how do we discover that? Well, all we need to do is use the theorem of Pythagoras here. So if we are calling this measurement r, so we could say r squared will equal the sum of the squares of each one of those segments. So our r squared would be 9 and 16, and that would give us 25. So the square root of 25 being 5. So that's what we know straight away. The r is 5. The length of that segment, or the modulus of this complex number, will be 5. So now we need to calculate that angle. So if we want to use that same triangle, look at the orange angle. Here we would say the opposite to this angle theta is 4, and now we have the hypotenuse or the adjacent side, but probably ideally we would always try to use these two because they are the ones given in our complex number in the rectangular form. So we could say that to find the angle, we would say that the tangent of theta would equal opposite over adjacent. So the opposite being 4 and the adjacent to the angle being 3. So we know that the tangent of that angle will then be 4 over 3, and that's when we have to use the inverse function. Tan inverse of 4/3 equals our theta. And then that's when we use the calculator and we discover that theta will equal, the calculator will give us the smallest angle possible, which in this case will be the -1, and we saw it there, negative 53.1 degrees. So it's important to note that the 5 would come out 5 anyway, even if we had used, of course, and we should probably do that, to use the original values of A and B. If we had used 3 squared plus -4 squared, which is our true imaginary part of that complex number, we would still get positive 16. So it makes no difference. The modulus of this complex number z and the complex number 3 plus j4 with positive imaginary part will be the same, the modulus, but the angle will be different because of the quadrant where our number is. So it's always important to draw the diagram, and now we can tell our answer here. For the original z equals 3 minus j4, we can say this is equivalent to, so we first write the modulus and then the angle theta. So the modulus is 5, and we use that symbol of less than, just like that, or also looks like an angle, negative 53.1 degrees. This answer could also be rewritten as 5. The 5 won't change because that's the length of that segment. We could use a positive angle if we wanted. So look at the orange angle here. What's the equivalent if we went that way? So the full lot would be 360, but if we do 360 and remove the 53.1, we are going to have the positive angle, which is 306.9 degrees. And of course we could also work with radians instead of degrees, and then we would just write 5 and the less than or the angle symbol and the angle in radians.